Okay, so let's now discuss the proof of the Bott periodicity theorem. Let me check if it works. Okay, so let's now discuss the proof of the Bott periodicity. So the proof we are going to discuss was given by Kuntz in 1982. Originally, it was given for C-star algebras only. But later it was discovered that this proof can be suitably modified so that it works actually for all Banach algebras and for some more general topological and chronological algebras. But for simplicity, we will follow the original argument given by Kuntz and discuss the case of C-star algebras. So we start with the Choplet's extension. So it has the following form. And we will slightly reduce this extension in the following way. We have the evaluation map here, the evaluation at the identity, which acts as the complex numbers. If we compose these two arrows, then we get a homomorphism from the Choplet's algebra to the complex numbers. That's denoted by epsilon. So we have such a commutative diagram. So the kernel of this evaluation map is just the algebra of functions vanishing at the identity. So we can interpret it in the following way. This is the kernel of this map. And the kernel of this map will be denoted by T0. So T0 is just by definition is the kernel of epsilon. This is a codimension 1 ideal in the Choplet's algebra. And this simple diagram shading shows that T0 still contains the compact operators, and we have the following extension. So the first line in this diagram is also a C-star algebra extension. Let's call it the reduced Choplet's extension. What we want to do next is to tensor the reduced Choplet extension by an arbitrary C-star algebra. And we want to be sure then that we will still have an extension. This is not entirely obvious, but this follows from the next general fact. Here we have a C-star algebra extension, IAB. C-star algebra extension, and assume that B is nuclear. B is nuclear. Then, for every C-star algebra C, the following sequence obtained by tensoring with C, I tensor C, A tensor C, and B tensor C, is also a C-star algebra extension. What is not trivial here? Well, it's more or less clear that this error is injective and this error is surjective. What is not entirely obvious is the exactness in the middle term. And the easy part of this theorem is a simple exercise, which tells us that the minimal C-star tensor product preserves injections and surjections. If we have two homomorphisms between C-star algebras from A1 to B1 and from A2 to B2, C-star algebra homomorphisms, and if both phi1 and phi2 are injective, respectively surjective, then so is their tensor product. This is a rather simple exercise. For the injectivity, this is more or less immediate from the definition of the spatial tensor product. We simply represent B1 and B2 faithfully on the Hilbert spaces. Composed with phi1 and phi2, we get faithful representations on A1 and A2 respectively. And we will see that this map is just isometric, so it is injective. And for the surjectivity, use the fact that the algebraic tensor product takes surjections to surjections, and so this implies that the image of this map is dense, but the image of any homomorphism between C-star algebras is closed, and so it is surjective. So what is not trivial here is the exactness in here. Here, this is the point where we need nuclearity. Again, we skip the proof because it involves some properties of nuclear algebras that we didn't discuss. But modulo these general facts, the proof is not very hard. So we now use this fact. We apply it to the reduced Topliss extension. Of course, this algebra is nuclear because it is commutative. So this implies that for every C-star algebra A, we have the following extension: K tensor A, T0 tensor A, and the tensor product of this algebra by A is nothing but the suspension over A, because this is just C0 over the real line. Let's look at the index map associated to this extension. So the index map takes K1 of SA to K0 of the tensor product of A by the compact operators. Well, K1 of SA is just by definition is K2 of A. This is our definition of K2 of A. And K-theory is stable, so K-theory of this tensor product is canonically isomorphic to K0 of A. So let's recall that this isomorphism takes every element, is induced by the map from A to this tensor product, which takes every element by the tensor product with any rank 1 projection in K. So composing these maps, we get a homomorphism, let's denote it by alpha, from here to here. And now what we are going to prove, and this is Kuhn's theorem, alpha is an isomorphism. So this is one of the several concrete forms of writing the Bode periodicity. So the Bode periodicity is induced by this index map. The proof will look like a chain of reductions. So we reduce our statement to other equivalent forms. The first reduction is as follows. Let's observe that it suffices to show that the K-theory of this algebra in the middle is trivial. That Ki of the tensor product of T0 by A vanishes. Well, indeed, if it vanishes, then we simply write the respective exact sequence. So we have, in the general case, we have K1 of this algebra here, and K0 of the same algebra here. And by the exactness of this sequence, and since we have 0 here and 0 here, this map is an isomorphism. So we will prove this statement. To prove this equality, we will introduce an auxiliary C-star algebra. Let's denote it by T hat. T hat will be a subalgebra in the tensor product of the toplets algebra by itself, and it has the following form. It is K0, K tensor T0 plus T tensor the identity. So it is a subalgebra in T tensor T. So clearly this is a star subalgebra. Star subalgebra. Well, this is an ideal in T tensor T. Here we implicitly use this exercise. So the spatial tensor product preserves subalgebras. So this is an ideal in T tensor T. This is a subalgebra in T tensor T. We take the algebraic sum and get a star subalgebra in T tensor T. Why is it a C-star subalgebra? This follows from the next simple exercise. If we have a C-star algebra A, a C-star algebra, C-star subalgebra B, B is a closed star subalgebra, and a closed two-sided ideal, I of A, closed two-sided ideal. The algebraic sum of B and I is closed in A. B plus I is closed in A. This is a simple and useful exercise in C-star algebra theory. A hint is to use the fact that the image of any homomorphism between C-star algebras is closed. Okay, so now we see that T hat is also a C-star algebra. Hence, T hat is a C-star subalgebra of T tensor T. And we have the following extension, which is more or less immediate from the definition of T hat. So K tensor T0 is an ideal in T hat just by construction. What can we say about the quotient modulo this ideal? Well, let's observe that these two subspaces have trivial intersection because we have identity here and T0 here. T0 doesn't. T0 has a trivial intersection with the identity. It is a codimensional ideal. So these two subalgebras have trivial intersection, and so the quotient modulo its ideal is isomorphic to the second summand. So the quotient is isomorphic to T. We know that T is nuclear, so applying this fact again, we can tensor this extension by A. K tensor T0 tensor A, T hat tensor A and T tensor A. So this is a sister algebra extension, and I claim that it splits. It splits by the following simple map, that's denoted by K. So K simply embeds T into the second summon here. So formally, K acts by the following formula. It takes B tensor A to B tensor 1 tensor A. Clearly, this is a section for this projection. So this is a split sister algebra extension. Also, to simplify things, let's remove the compact operators from here. So formally, we have a canonical map from here to here, which takes every element in this tensor product, say little x, to the tensor product with the rank 1 projection E00. So this is how the vertical arrow acts. And let's now denote by J the composition of these two maps. What can you say about J? Well, this arrow induces an isomorphism in K-theory because K-theory is stable. So this induces an isomorphism in K-theory. And this map induces an injection in K-theory because the extension splits and K-theory is split exact. So this implies that J star from Ki of this algebra to Ki of T hat tensor A is injective. Here we use the fact that Ki is stable and split exact. Okay, now we have our next reduction. To complete the proof, it suffices to show that J star is 0. It suffices to show that J star is 0. Well, indeed, if it is 0, and we already know that it is injective, this implies that this group is trivial, and this is exactly what we want to prove here. So now we have to prove that the J star is trivial. To prove that J star is trivial, we will need to construct another map from this algebra to this one. And it is constructed as follows. First of all, let's make a little observation. If A is a unital C-star algebra, and little u is an isometry in A, then an isometry induces an homomorphism from A to itself, namely the following map from A to itself, which takes every element little a to u, A, u star, is a star homomorphism. Well, simply apply it to the product AB and use the fact that u star u is 1. Since u star u is 1, we simply calculate that this is indeed a star homomorphism. We call this map the conjugation by u. If u is unitary, then this is the Ginian conjugation, ua u inverse. But even if u is not unitary, just an isometry, it's still a star homomorphism, not necessarily an automorphism, but nevertheless it is a star homomorphism. So let's call it conjugation by u. Okay, so this was just a little observation. Let's now consider the following map. Let's denote it by psi. This will be the map from T hat tensor A plus, unitization of A, to itself, T hat tensor A plus. So let it be the conjugation. Let it be the conjugation by the following element: V tensor 1 tensor 1. So V tensor 1 sits in T hat, and this identity is the identity in A plus. So clearly this is an isometry because V is an isometry. Let's observe that we can restrict psi to the tensor product of T hat and A, so remove the plus here, and it is invariant under psi. This is more or less obvious because we have an identity in the last tensor sign, and so when we conjugate by this map, it takes this algebra to itself. Let's now construct another map from this algebra to this one as follows. We take K, we restrict it to T0 tensor A, and compose it with the conjugation psi. And the composition will be denoted by psi1. Psi1 is K composed with psi restricted to T0 tensor A. So it acts from T0 tensor A to T hat tensor A. So we have two maps between these algebras, psi1 and J. Our next little goal is to show that these two maps are orthogonal in the following sense. So let's give a definition. Suppose we have two C-star algebra homomorphisms, say phi from A to B, and psi possibly from another algebra A prime to B. We say that they are orthogonal and write the following symbol if the product of their images is 0. If phi of A, psi of A prime is 0. Or equivalently, we can take the product in the opposite order. And this is equivalent because, well, we just can apply the involution. If we apply the involution to this equality, we get this one. And it's a simple exercise to show that if we have two orthogonal homomorphisms, phi and psi, suppose now that they act from A to B, and that they are orthogonal. And then first of all, their sum is also a star homomorphism. Phi plus psi is also a star homomorphism. Of course, in the general case, the sum of two star homomorphisms is not a star homomorphism. It is not necessarily multiplicative. But if they are orthogonal, then their sum is also a star homomorphism. And what is important here is that the induced map in K-theory, phi plus psi star, is just the sum of the induced maps phi star and psi star from Ki of A to Ki of B. This is a rather simple exercise. First of all, everything can be reduced to K0 by using suspensions. And in the case of K0, simply apply phi and psi to the K-theory classes of projections into unitization of A, and use the fact that phi and psi are orthogonal. Okay. So now, coming back to our concrete situation, I claim that psi, which acts from this algebra to itself, and J are orthogonal. And this is a very simple calculation, just a line. So I'll leave this as an exercise for you, but this exercise is absolutely elementary. Psi and J are orthogonal. Basically, this follows from the fact that if we write this explicitly, then this follows from the fact that E0, 0 times V is 0. So if we apply the right shift and then project onto the first coordinate, we get 0, of course. This equality easily implies that psi and J are orthogonal. So now let's look at psi 1. Of course, then psi 1 and J are also orthogonal because, there is an obvious typo here. Of course, first we apply the map, when we compose the maps, then the first map is on the right and the second one is on the left. So first we apply K. I'm sorry about this typo. First we apply K from here to here, and then compose with the conjugation, which acts in here. So the correct formula is like this. This is psi 1. Okay, so of course the image of psi 1 is contained in the image of psi. And so since psi and J are orthogonal, we deduce that psi 1 and J are also orthogonal. And psi 1 is orthogonal to J. Well, they act between the same C-star algebras from this one to this one. Both psi 1 and J act from here to here. And we apply the previous exercise. And let's consider the sum. Let's denote it by psi 0. So psi 0 will be J plus psi 1. So by this exercise, psi 0 is also a star homomorphism. Is a star homomorphism. And psi 0 star is J star plus psi 1 star. And now we have our next reduction. We want to show that J star is 0. This is our goal. We want to show that J star is 0. This means that this one is equal to this one. How can we prove that they are the same? Well, probably you have already guessed that if I denote if I equip two objects with subscripts 0 and 1, probably this is a hint that these two objects are homotopic. And this is indeed the case. Now observe that it suffices to prove that J star is 0, it suffices to show that psi 0 and psi 1 are homotopic. And this is our next reduction. If we show that they are homotopic, then by the homotopy invariance of K theory, the induced maps psi 0 star and psi 1 star are the same, and so J star will be 0. In order to prove that they are homotopic, we may assume without loss of generality that our algebra A is just the complex numbers. So we may assume from now on that A is just the complex numbers for the following reason. If we look at the construction of our maps, psi 0 and psi 1, well, we see that psi 1 constructed out of A is nothing but the tensor product of psi 1 constructed for the complex numbers times the tensor of the identity map of A. This follows from the construction. The same is true for J. J constructed for A is J constructed for C times the identity map of A. And taking the sum of these two maps, we see that the same is true for psi 0. 0A is psi 0C tensor the identity map. So as a result, if these two homomorphisms are homotopic, this really implies that these two homomorphisms are also homotopic. So it's now suffices to consider the case where A is the field of complex numbers. So now our maps psi 0 and psi 1 act from psi 0 and psi 1 act from T0 to T hat. Let's now extend it to unital homomorphisms defined on T on the Toeplitz algebra. Let phi 0 and phi 1 denote their unital extensions to the Toeplitz algebra. Their unital extensions to the Toeplitz algebra. Why is it possible? Well, it's more or less immediate from the definition that the Toeplitz algebra is nothing but the unitization of T0. T0 is a codimension 1 ideal, a codimension 1 two-sided ideal in T, and so its unitization is isomorphic to T. So by the universal property of the unitization, we may extend psi 0 and psi 1 to the Toeplitz algebra. Why is it useful? We have to keep in mind the universal property of the Toeplitz algebra. So to define a homomorphism from the Toeplitz algebra to another algebra, it suffices to take V to a suitable isometry. And then the universal property of the Toeplitz algebra gives us a homomorphism from the Toeplitz algebra. So to construct the homotopy between phi 0 and phi 1, let's look at the images of the canonical generator of the Toeplitz algebra. Let's denote these images by V0 and V1 respectively. So let V0 be phi 0 of V and V1 phi 1 of V. It's useful, well, it's not strictly necessary, but to understand better these elements, it's useful to characterize them as suitable operators. And to do this, let's represent the algebra T hat faithfully on a suitable Hilbert space. So let's recall that T hat is contained in T tensor T. T is already faithfully represented on the little space. And so this tensor product is faithfully represented on the tensor product Hilbert space, which is nothing but the little 2 over the product of non-zero integers by itself. Let's now look how the respective operators V0 and V1 act. So V0 and V1 act. So it's enough to explain how they act on the standard orthonormal basis. On the orthonormal basis consisting of such elementary tensors, I and J. This is an orthonormal basis of the space. So they act as follows. As follows, and actually this is simple exercise, which is a little calculation. So I just draw pictures. We can write formulas, but probably the picture is more informative in this case. So we represent elements of our basis as such dots on the plane. So this is the I-axis and this is the J-axis. So V0, this will be, oh, sorry, let's start with V1. V1 is a bit easier. V1 acts as follows. it fixes every element in the first column and acts at the remaining part of the picture as the horizontal shift. So this can be checked by an explicit calculation. We have an explicit formula for phi 0 and for phi 1, sorry, at this here we work with phi 1. We have an explicit formula for phi 1, and using this formula, and we can obtain some expression for V1 and apply it to the canonical basis of our space. So this is the picture which explains how V1 acts. Let's now look at V0. V0 is slightly more interesting. It acts on the first column as the vertical shift of this form. And it acts on the remaining part of the picture as the horizontal shift. This is V1, V0. So by looking at these pictures, we see that both operators, V0 and V1, are not very far away from the horizontal shift. So the only difference is in the first column. The first columns are different, but the remaining part of the picture is the horizontal shift. And we can actually reduce them to the horizontal shift as follows. Next exercise, which is also absolutely elementary, that V0 can be written as U0 times the horizontal shift. So V tensor 1 is nothing but the horizontal shift. So V acts on the first coordinate, shift is to the right, and it doesn't change the second coordinate. So this operator is the horizontal shift. And U0, well, I'll explain what U0 is in a moment. And V1 is U1 times V tensor 1, where the operators U0 and U1 act as follows. Again, I draw a picture. And again, I start with U1 because it is a bit easier. So U1 flips the first and the second columns. So the picture looks like this. And it acts as the horizontal shift at the remaining part of the picture. In the remaining part of the picture, the situation is like this. Well, this is more or less elementary. If we compose this one, and sorry, not this one. If we compose the usual horizontal shift with this operator, we get this picture. How about V1? So this is this is V1. This is U1. This is U1. And U0 looks as follows. It is slightly more complicated. So the picture is as follows. It flips the first and the second columns diagonally in this way. These two elements are interchanged. And so on. Here we have the horizontal shift. And this element is fixed. This is how U0 acts. Again, if we simply define U0 by this picture and compose it with V tensor 1, we easily obtain this picture. This is an absolutely elementary exercise. Okay, so U0 and V1, why are they better than V0 and V1? They are better because they have a simple structure. First of all, obviously they are unitary. And they are symmetries, they are involutions. If we apply each of them twice, we get the identity map. Also, it would be nice if they belong to the same algebra. It is not immediate from the picture that they also belong to T hat. But in fact, they do belong to the same algebra. And this is our next exercise. And this is the point where I have to look into my notes, because I have to write a formula which is almost impossible to remember. U1 is given by the following formula: V squared, V star squared tensor 1 plus E00 V star tensor 1 plus V E00 tensor 1. This is U1, and U0 is the same. The first summand is the same: V squared V star squared tensor 1 plus E00 V star tensor V plus its adjoint V E00 tensor V star plus E00 tensor E00. Again, the verification is absolutely elementary. We just compare this picture and these formulas. Roughly, for example, if we look at U1, the first summand is responsible for this part of the picture. So it shifts all these vectors to the right, and it cancels the first two columns. So this operator V squared, V star squared cancels the first two columns. And the remaining part, this sum, is nothing but an operator which flips the first and the second columns and cancels the remaining part. So if we combine them, take the algebraic sum, then what we get is exactly U1. And similarly for the second line, this is the same operator which cancels the first two columns and shifts the remaining part to the right. And so this part is responsible for this diagonal flip. And the final summand E00 tensor E00 is responsible for the part which fixes the lower left corner, this vector. So I hope this is quite convincing. In fact, we can avoid using pictures, and we could simply define U0 and U1 by these formulas, but in this case it's absolutely impossible to understand where they come from. So essentially they come from these pictures. Okay, so now by looking at these formulas, we easily see that, of course, this operator sits in T tensor the identity. So all these operators, this one, and this one are in the Toeplitz algebra, and this is contained in T hat. So let's recall that T hat, so let me write it down again. T hat, by our definition, T hat is K tensor T0 plus T tensor the identity. So all these operators sit in here. And this operator, so this part also sits in T tensor C1. And this operator clearly belongs to K tensor T. This operator is compact, it is a rank 1 operator. This is compact, and this is of course also compact. And these three operators V, V star, and E00 are in T. So this sum sits in K tensor T, and it's a sub-exercise to show that this is contained in T hat. So every element in here can be decomposed as the sum of two elements. One of them is in here, and the second one is in here. Okay, so as a result, we see that both operators, U0 and U1, belong to the algebra T hat, which is very nice. So what can we say about these operators? Let's observe that they are unitary. Every operator UK is unitary. and UK squared is the identity mapping. This is true for 0 and for 1. Why is it useful? By using this property, we can easily construct a homotopy between U0 and U1. So we have the following lemma. If A is a unital C-star algebra, and U is an element of this form, which is unitary, and U squared is 1, then U is homotopic to the identity. And the homotopy is quite explicit. It is given by the following formula: 1/2 times 1 plus U minus 1/2 times the following exponent, 1 minus U. And I claim that this is clearly a path from if t equals 0, then we have 1 plus U minus 1 plus U, so this will be U from U. And if t equals 1, we have the plus sign here, and the sum will be equal to the identity, from U to the identity. So this is clearly a path from U to the identity, and a simple calculation shows that every element in this path is unitary. Every UT is unitary. This is an explicit calculation, a little exercise. So this completes the proof of the lemma. Well, of course, here I didn't write this. I mean that they are homotopic in the unitary group, of course, in the unitary group of A. Let's now apply this to our elements U0 and U1. So each of them can be connected to the identity, and so they are homotopic. Applying this lemma, we deduce that U0 and U1 are homotopic. Are homotopic in the unitary group of T hat. Let's take let's choose a homotopy. Choose a homotopy. Let's denote it by UT, the path of unitaries, path in the unitary group from U0 to U1. Well, let's now come back to the elements V0 and V1. So by using this path, we easily obtain a path from V0 to V1. Respective path is just UT times V tensor 1. And this is the path of isometries. The path of isometries from V0 to V1. Well, clearly the product of an isometry and the unitary element is an isometry. So each element in this path is an isometry, and we get a path of isometries. A path of isometries is the same thing as an isometry. An isometry, as denoted by W, in the algebra of continuous functions from the interval 0, 1 to the algebra T hat. Clearly, an isometry in this algebra is the same as the path of isometries in this algebra. Okay, let's now use the universal property of the Toeplitz algebra. There is a unique star homomorphism, let's denote it by big phi, from the Toeplitz algebra to this one. Which takes the generator V to W. Phi of V equals W. Now this is almost the end of the story. What happens if we compose this homomorphism with the evaluation at 0 at the identity? Well, if we apply this to V and then evaluate at 0, this is, well, this is just W of 0. W of 0 is V0. This is V0. And similarly, if we evaluate at the identity, we get, oh, sorry, not W, V. First, we apply to V. Phi of V is W, and the evaluation of W at 0 is V0. And similarly, if we apply, if we evaluate at the identity, we get V1. Okay, now let's recall that a homomorphism from the Toeplitz algebra is determined by the image of V uniquely. So by the uniqueness of such a homomorphism, we deduce that this composition is little phi 0, because phi 0 also takes V to V0. And similarly, this composition is little phi 1, again, because phi 1 also takes V to V1. We deduce that phi 0 and phi 1 are homotopic. If we restrict them to T0, we deduce that psi 0 and psi 1 are homotopic. And this is the end of the proof. We remember that our final reduction was to show that these two maps are homotopic. If they are homotopic, then J star is 0. And if J star is 0, then the tensor product of the reduced Toeplitz algebra by A has trivial K-theory. And this implies, finally, that the homomorphism alpha from K2 away to K0 away is an isomorphism. So this completes the proof. One final remark about the Bott periodicity, maybe two final remarks. First of all, the advantage of Kuntz's proof is that it can easily be adapted to a more general situation. Actually, essentially we didn't use any specific properties of K-theory except for its half-exactness, stability, and homotopy invariance. And slightly modifying this proof, we can show that every functor from C-star algebras to abelian groups which satisfies these three conditions, namely half-exactness, stability, and homotopy invariance, also satisfies the Bott periodicity. And the second remark is that the inverse map to alpha has a very useful concrete characterization. At this point, it's now essential that we deal with K-theory. This is a so-called Bott map. And it also can be described explicitly as follows. So I omit some details. Details will be given in the exercise sheet. But roughly, it acts as follows. You have a projection over A, or more exactly, a projection in the matrix algebra. Then we can construct a loop Fp here, well, for simplicity, I assume that A is unital. Everything is reduced to the unital case. If A is unital, then every projection in A gives us a map Fp from the circle to the unitary group Un of A. Given by the following simple formula, Fp of Z is Zp plus 1n minus p. And the Bott map is well defined by the following rule. It takes the K-theory class of P to K1 class of Fp of this loop, which sits in K1 of the suspension of A, which is nothing but K2. So K1 of the suspension of A consists of equivalence classes of matrices in GL infinity of SA, and each such matrix can be each such matrix comes from a loop in the unitary group of A of suitable size. And it can be shown that if we define the map beta in this way, it will be indeed the inverse of alpha. And the very final remark is that this map beta has actually it has a geometric origin. One can show that for every pair of C-star algebras, we can define a map from the so-called exterior product from Ki of A times Kj of B to the K theory of A tensor B, where the sum is taken modulo 2. Basically, if we apply it to projections, this is just the tensor product of projections. Now, the bot map can be characterized as follows. It acts from K1 of the algebra of continuous functions of C0 of R2 times K0 of A to K1 of the tensor product of these algebras, and the tensor product of these algebras is nothing but there's a typo here, K2 of course, K2. That's not correct. Let me write it down here. So it acts from K2 of C times K0 of A to K2 of A. So what is K2 of C? K2 of C is K0 of C0 of R2. The bot map takes every element in K0 of A, that's noted by mu, to the exterior product of X and a suitable element in here, which has a very clear geometric interpretation. This is a so-called bot element. To define this element, let's say call that K0 of C0 of R2 is contained in K0 of its unitization, and its unitization is C on the sphere. So this is just the topological K theory of the sphere. And the bot element comes from two line bundles over the sphere. More exactly, this is the difference of the K theory class of the dual of the canonical line bundle over the sphere, the dual of the Hopf bundle, minus the trivial one-dimensional bundle. So both elements sit in here, but since they have the same dimension, the difference sits in here. And this is the so-called bot element. So the bot isomorphism from here to here is given by the exterior product by the bot element, which is interpreted in terms of vector bundles, by this formula. This can be proved by an explicit calculation, and by using this interpretation of the bot isomorphism, if we now come back to our examples that we discussed today, when we calculated K-theory of the sphere, for example, and of the torus, we can use the Bott isomorphism and the explicit form of the Bott isomorphism to describe the generators of the respective K-theory groups explicitly. In particular, K0 of the sphere, we remember that it is z squared. So, in fact, it is generated by these two elements, this one and this one. So these are the free generators for K-theory of the sphere. Okay, and so this is the end of our course. Thank you for coming. Спасибо. До свидания. Ну тогда как с курсовой вас дойду руки, тогда в общем сигнализируйте.
Я так представляю, что это будет выглядеть так. 16 у меня курс закончится.
Давайте я остановлю пока, чтобы никто не поставил.